Jinyoung part will tell us about thresholds of properties in random graphs, and in particular about that property of the Hamiltonian cycle.
Okay. Thank you very much. Thanks for coming to this talk. And I heard from Avi several times that our group is pretty diverse. So I will try to be slow and with lots of examples. And if there are any questions, please feel free to stop me, interrupt me anytime and ask questions. Okay, please. Okay, so today's talk is about the threshold for the square of a Hamilton cycle, and this is showing to work with Jeff Kahn and Bhargav Narayanan. And this topic will be the second part of my talk. So this is a two-hour talk, yeah. And in the first part, I will introduce some background, mainly the meaning of the thresholds here. And then I will introduce Kahn-Kalai conjecture and a recent result of Frankston, Kahn, Narayanan, and myself. So basically, my purpose for the first part is to put the main work in some interesting context. Okay, so here comes some basic definitions. First, we use X for a finite set, and 2 to the X for the collection of subsets of X as usual. And we use mu P for the P-biased product probability measure on 2 to the X. So this means we have 2 to the X here, and whenever we choose a subset of X, then its measure is defined in this way. So the usual thing. And we use XP for the random variable whose distribution has mu sub P. So for example, if our universe X is n choose 2, which is the set of edges of the complete graph Kn with n, this usual set, the set of numbers from 1 up to n, then our random variable xp is just GNP, which is the Erdős-Rényi random graph. So GNP means we have n vertices. So that means we have potentially n choose 2 edges, and we choose each edge with probability p independently. So in this way, we get some random sample of the graph. Okay. Are you okay so far? Okay.
Yes.
Thank you, Lisa and Avi. Okay, and so for example, because I promised I will give you lots of examples. For example, if our universe is this n choose 2, then 2 to the x looks like this. So we have the empty graph at the bottom, and we have the complete graph on the top. And for example, the measure or the probability for this empty graph is 1 minus p to the n. And the probability for the complete graph is p to the n. And so on. Okay, and we use f, a subset of the collection 2 to the x. We say f is an increasing property if f looks like this here. Okay, so rigorously, this means whenever we have a set B, which contains a member in F, then this B is also in F. Okay, and note that the measure of F is just the probability that our random variable XP is contained in this property F. This is also the same thing. And finally, we use with high probability if the probability for this event tends to 1 as n goes to the infinity. So these are all of the basic definitions. And are there any questions?
Here, n is the size of your set or some parameter with which?
No, n is just, so in general, n will be the number of vertices in a graph. But because we take our x, for example, in this case, the set of edges, so n is not necessarily the size of the universe. So in this case, the size of the universe will be n choose 2. Yeah, that's why I wanted to separate n and the size of x. But thanks for your question. Okay. Then let me define the threshold. And so first of all, we always assume that f is increasing, and this is not the empty family or the entire family, just to remove some trivial cases. And if we assume this, then an exercise for the experts, and easy exercise is this. Given f, the p measure of f is strictly increasing in p. So for example, if p is 0 and f looks like this, if p is 0, then that means the measure of the empty set is 1. So this gives the p measure of f is always 0. On the other hand, if p is 1, then the measure of x will be 1. So this gives us the p measure of f is always 1. And if p is in the middle of 0 and 1, then the p measure of f is in the middle of 0 and 1, and it's always strictly increasing. So we have this graph here. So as p increases, mu p of f also increases. So the graph looks like this. And now the definition of the threshold is this. Because this graph is continuous, so there must be some point p such that the measure mu p of f is exactly 1/2. And this is the definition for the threshold for f. So given an increasing family f, there is some probability p such that the measure of f is 1/2. And we call that probability p the threshold for f. Okay, so this is really the threshold, which means if p is larger than the threshold, then that means f is a likely event. F is likely to happen. On the other hand, if our probability p is smaller than the threshold, then this f is unlikely to happen. So this is why we call this p the threshold. And a central question in probabilistic combinatorics, or the central question in probabilistic combinatorics, is this. Given an increasing property f, what's the threshold for f? So that means for what probability p is it likely or is it unlikely that f happens? Okay, so this is our central question for today. And are there any questions? Cynthia, you're smiling. Is that a good sign or a bad sign? Okay, thank you. Okay, so as promised, here are some examples. We will see 4 examples in the first part. First, so here our universe is n choose 2. So our universe is the set of edges in the complete graph. So our xp is GNP, the random graph. And let's say H is this small graph. And our property is to contain H. Namely, here we have the space q to the x, the space of graphs. And we have a bunch of copies of H's here. So here H, another H, another H. So because we consider a graph a labeled graph, so there are a bunch of copies of H's. It depends on the choice of the vertices. And this F looks like this, offset generated by these copies. So this is our F. So this means as soon as we pick an element here, then we have some graph which contains a copy of H. Okay, and we are interested in the threshold for this property F. So example 1, what's the threshold for GMP to contain a copy of H? Namely, what's the threshold for F? And let me introduce one more notion of threshold here. So we say P0, which is a function of n, is a threshold or Erdős-Rényi threshold if this probability goes to 0 in this range of P, and this goes to 1 when P is in this range. So maybe you are more familiar with this definition of threshold because this is more traditional thing, but the basic theme is the same. So we have this probability P0, so this time this is a threshold. And this definition says that if P is in this range, then F is likely to happen. And if P is in this range, then F is unlikely to happen. And so dot threshold is kind of like more refined notion of a threshold, but the famous Bolobash-Thomason result says that our dot threshold is actually a threshold. So when we look at the definition of a threshold, then the constant factor does not matter. For example, if P0 is a threshold, then 100 times P0 is also a threshold. So if we just care about a threshold, then we don't have to care about a constant factor of the threshold. So in the rest of the talk, we will just focus on the order of this refined notion of the threshold. Okay? Are you okay? Any questions? Okay, so then let me continue with this first example. What's the threshold for GNP to contain H? So the usual suspect is the expectation calculation. So for example, if we count the number of copies of H in G, so we have this G
So
and...
doesn't it depend on H?
I'm sorry?
Doesn't the threshold depend on what H is?
Oh yeah, sure, of course. It depends on the minimal elements. So if H changes, then of course the threshold changes. And we will see 4 examples regarding that. Thank you for the question.
Yes, every H defines a different property.
Yes, exactly. Yes. So we'll see some examples. Anyway, so here this H is this specific graph. Looks like this. Okay, so here we want to the threshold. Sorry. Here we consider the expected number of H's in G. So in G we have potentially n choose 4 copies of H. It depends on the choice of the vertices of H. So this is the number of potential copies of H. And then because H have 5 edges, so the probability for each copy of H to appear is exactly p to the 5. So the expected number of copies of H in G and P is n to the 4 times p to the 5, which goes to 0 if p is much smaller than this, and it goes to the infinity if p is much larger than this. So this says the threshold for the expectation is more or less n to the negative 4 over 5. So, and this expectation calculation gives us a trivial lower bound on the threshold, because if the expectation goes to 0, then that means there is no copies of H's in G and P with high probability, right? Because for example, extremely, if the expectation is 0, then that means there's no copy of H in G and P. Okay, so that means when P is, let me write it here, when P is much smaller than n to the negative 4 over 5, then the expected number of copies of H tends to 0. So that means with high probability, G does not contain a copy of H. Okay, and the threshold means if P is higher than the threshold, then G is likely to contain a H, so this quantity gives a trivial lower bound on the threshold. And it turned out the truth for the threshold is exactly this. It needs some argument, but because this is just an example, so let me not justify this. But here, what one can learn from this example is, so at this point, we may dream that, okay, this expectation calculation may predict the precise value of the threshold, because in this, at least in this example, this trivial lower bound from the expectation calculation gives us the truth. But of course, you see that this will not be true eventually. Anyway, so this was the first example. And let me move on to the second example. So in this example, K, another graph looks like this. And again, we ask the same question. What's the threshold for G and P to contain a copy of K? Okay, so we do the same thing. What's the expected number of Ks in G and P? First, we have n choose 5 potential copies of K, because K has 5 vertices. So the number of choices for 5 edges is n choose 5. And the probability for each copy of k is p to the 6 because k has 6 edges. And so this gives us the threshold for the expectation is more or less n to the negative 5 over 6. Okay, so if p is above this value, then the expectation goes to 0. And if p is above, what did I say? P is below this value, then the expectation goes to 0. So this this gives us a trivial lower bound on the threshold of f. Okay.
So this does not care about what the structure of H is, right? So
it depends.
So you can have like you can have nice like you can have H as a very interesting graph like a Ramsey graph or something, but it's still giving you something. So I don't understand it. Like if you have like H as a triangle, say, then it should have a different proof of existence than, let's say, a Ramsey graph in GMP.
Oh yeah, the Ramsey graph is another serious topic, and I don't want to talk about in this stage. But so here, at least for the
Let me comment on the question that I think is interesting. It is clear from the calculation that the only thing that matters for the expectation is how many vertices and how many edges. And there are very different graphs with the same number of edges. And you know, the answer may be different for them. The expectation only look at these numbers. Yes.
I see.
And eventually we'll see that now what we are doing is something wrong. But there's some problem with this calculation. Anyway, okay, so at least for the expected number of copies of k, we have this threshold. So the question is this trivial lower bound is the truth? And I think this question is not fair to the audience because the answer is right next to the question. So the answer is no. And it turned out the truth is the threshold for this property containing k is in the order of n to the negative 4/5. And do you see why? So here, this is 0. And the threshold for the expectation is n to the minus 5 over 6. But now I'm claiming that the truth is much larger, n to the negative 4 over 5. Why? It has to do with the previous example. Okay. So in this previous example, sorry, we looked at H, where H is this. And here, H is a subgraph of K. That means if we want to contain a copy of K, then we must contain a copy of H. And because the threshold for H was this, so the threshold for K is at least as large as the threshold for H. Okay, so here the lesson is, okay, the question is, then what about our dream? We dreamed that the expectation calculation predicts the threshold for F, but it looks like it was not. So what's the problem? The issue was we are looking at the wrong thing. Okay, so to get the answer, the right thing that we should have looked at is a copy of H inside K, not the K itself. Does this make sense? And so this says that as long as we look at the right thing, then the expectation calculation gives us the answer. So, okay, so our dream is not shattered yet. It will be shattered in the next slide. Okay, but are we okay with this example?
Yeah, it is great. I think that the point is the next dream at this point. The next dream is that we look at all subgraphs of our graph and we look for the maximum threshold of them and hope that the expectation for it will predict the threshold.
Yeah, but that's not true, unfortunately. Okay, so this is the next thing. So here we look at the perfect matching, which means we have a set of edges which covers all of the vertices. So this is a spanning graph. And again, we ask the same question. What's the threshold for G and P to contain a perfect matching? And So now I think you are an expert of this calculation. The expectation calculation gives us something like this. So we see that the threshold for this expectation is more or less 1/n. So my question is, okay, so from here we have a trivial lower bound on PC. Then the question is, okay, then does this give us the truth? And the answer is no. And it turned out the truth is this. The threshold for this property is log n times the lower bound, 1/n. And here, if we consider, as Avi said, even if we consider all of the subsets, we'll get the same expectation calculation. So really, the expectation calculation gives us 1/n. But the truth is log n far from the lower bound.
What happens you look on at h as the of
I'm sorry.
Yeah, I wanted to ask what happens if you look only on graphs of which must be of constant size.
Just a second. Just a second, there is some noise. Maybe Jinyoung, because you have two devices open or something?
No, I think it was another
thing. Yeah, Zoom problem. Okay, so yeah, go ahead.
Okay, yeah, I wanted to ask what happens if you look only at h's of constant size.
Oh, okay. In that case, yes, the truth is the expectation threshold will give us the truth. And that's a part of Kahn-Kalai, not Kahn-Kalai, that's the part that's implied by our result, joined with Frankston, Kahn, and Narayana. Yes.
Thanks.
No problem. Okay, are we okay so far? Okay. So where are we? Okay, so we were considering this perfect matching, and it looks like our dream is shattered. Yeah. So let's see one more example. So in this example, there was a log n gap between the lower bound and the truth. And let's take a look at one more example. So now we are considering triples. So here our universe is n choose 3. So we consider all of the possible triples. And so XP is a random 3 uniform hypergraph, which means we choose each triple with probability P independently. And the same question, so what's the threshold for H? So okay, I'm sorry, H is this random hypergraph. And what's the threshold for this random hypergraph H and P to contain a perfect matching? And again, a perfect matching here means we have triples, disjoint triples, which cover all of the vertices. This was a famous problem. It's called, excuse me, Shamir's problem from 1980s. And again, here, if we do the expectation calculation, then it gives us a trivial lower bound n to the -2. But it turned out the truth is, the threshold is n to the -2 times log n. So again, there is a log n gap. So this is a famous and serious result by Johansen, Kahn, and Wu from 2008. Anyway, so the point is, in this problem, we again see this log n gap. So what's happening here? So let me explain why we have log n over n, why this log n over n should be the truth. So we are going back to the example 3, the threshold for G and P to contain a perfect matching. So let me remind you that first, we have the threshold for the expectation 1/n, but the truth, the threshold was log n over n. And here, actually, this log n over n is another trivial lower bound on the threshold. So we said this is a trivial lower bound by the expectation calculation, but actually, this one is again a trivial lower bound. And this is because of the coupon collector problem. I guess you all know what it is, but let me explain this. So this is simple. So we have n coupons out there. And each time we buy a box of cereal, we get a coupon randomly. So the question is, if we want to collect all of the n coupons, how many cereal boxes do we need to buy? Or we don't buy cereal boxes. How many boxes of cereals do we need to buy? And So yeah, this is a famous question, and the answer is we need at least in the order of n times log n serials or boxes to collect all of the coupons with high probability. And if we apply this to our problem, then in this case, the coupons are the vertices. We have n vertices, and the serial boxes are the edges. So in GNP, we choose each edge with probability P, which means it's like we are throwing some random edges like this, right? And each time we throw an edge, we hit some vertices, which means we collect some coupons. Then to hit all of the vertices, we need more or less n times log n edges, which corresponds to the probability in the order of log n over n. Okay, so that means if P is much smaller than log n over n, then with high probability, typically there is some isolated vertices. This means there's no perfect matching, right? Because a perfect matching is a spanning graph. So here we see that log n over n is another trivial lower bound. So the actual task is to show that this trivial lower bound is an upper bound. Okay, so far we've seen 4 examples, and let me remind you that our main question is to figure out what the threshold is. So the question is, what drives the threshold? The first 2 examples showed that the expectation calculation gives us some hint for the threshold. And the latter 2 examples gave us this coupon collector H behavior gives us the log n gap between this expectation calculation and the actual threshold. And combining those 2 observations, Kahn and Kalai made this beautiful conjecture. This is a rough statement, and I will give you a more rigorous statement later. So it says that for any increasing family F, the threshold for this increasing family is at most log n times the threshold for the expectation. So basically it says that the 2 factors, the expectation calculation and the coupon collector H behavior, are the only factors that decide or that traps the actual threshold. So this is a beautiful conjecture, and it's still open. So are you okay with this conjecture? Are there any questions?
I'll just say that knowing Kahn-Kalai for many years in particular, I think they made this conjecture, and maybe they even said in the paper that they are not sure they believe it. It seems too strong to, and of course I know they try to refute it a lot. So yeah, it's a very bold conjecture.
Yeah, so I still remember how much I was excited when I saw this conjecture first. Anyway, so this conjecture is still open, but we proved some fractional version of this conjecture, which is again some like as strong as this conjecture so far. So the next part.
Another comment, Jinyoung. I just want to mention for context that the same question, this looks like probabilistic graph theory, but exactly the same questions come up in statistical physics. Lots of examples where you're looking for thresholds of graph properties happen in statistical physics. They are interested in critical probabilities just as much.
Okay, thank you. Okay, are there any questions or comments? Okay. So next part, I will give you a rigorous statement of the Kahn-Kalai conjecture. And for that, we need this rigorous definition for the expectation threshold. So as Avi commented, to get the right expectation threshold, we have to consider all of the possible subsets of the graph. But actually, okay, so this definition is motivated by that observation. So we call that the threshold is P, is the probability P which satisfies this property. So we have this increasing property F, and for the threshold, at the threshold P, the mu P measure of F is exactly 1/2. And for the definition of the expectation threshold, the motivating example are the first 2 examples. For example, in the first example, we considered this graph H. And the expectation calculation was more or less n to the 4 times p to the 5, where n to the 4 is the potential number of copies of H. And this is the probability for each H to appear. Okay, so now one more definition, one more notation. Given a collection G, we use this for, okay, graphically this. We have some family G, and this notation means the offset generated by H, which means we choose all of the sets which contains at least one element in G. So this definition exactly says this picture. This is our offset generated by G. Okay, then here comes one observation. This Q gives a lower bound on the threshold if there exists some collection G in 2 to the X such that first, the offset generated by G contains F. So again, this definition is motivated by this observation. So you can think of G as a collection of H's and so on. Anyway, so the first item says that the offset generated by H contains F. And the second condition is this quantity is bounded above by 1/2, where this quantity exactly corresponds to this expression, right? So here, G corresponds to, in this example 1, G corresponds to the set of copies of H's. And this calculation corresponds to the number of copies, n choose 4, times p to the 5. Okay, and this 1/2 is exactly the threshold. You know, the threshold for the expectation is where the two values split, 0 or the infinity. Okay, and let me justify this observation. If this happens, then Q gives a lower bound on PC because of this. So for this, we just need to show that mu Q, the Q measure of our increasing family F, is at most 1/2, right? If this is exactly 1/2, then Q is the threshold. But if this is less than 1/2, then that means Q is smaller than the threshold because we have to push up the probability to achieve 1/2. Okay, but then how do we show this? First of all, this is, of course, the Q measure of G because of the first property. And then by the union bound, this is at most summation for any S in G, the measure of the offset generated by S. So this means we have this G, and this part is, offset generated by H. And in this calculation, what we use is we just add up all of measures of these sets. So this is the union bound, and this gives an upper bound, a trivial upper bound on the second expression. And finally, what's this? This is just exactly Q to the S, which is here. So by 2, we have, this is at most 2, 1/2. Okay, so this was a justification of this observation, but just intuitively, we don't even need this numerical justification. It just says that, oh yeah, Q is too small to be a threshold, to be the threshold. Anyway, and then after this, we take QF. This is the this is the expectation threshold. We take Q to be the maximum of such Qs, maximum of the Qs which has such G. Then it gives a trivial lower bound on the threshold, right? Because every such Q was a lower bound. So even if we take the maximum, this is still a lower bound. And so this is the definition for the expectation threshold, whose definition is motivated by this example and the second example. right? In the second example, just considering the minimal elements was not enough. So in the second example, we learned the lesson that we have to consider all of the sets below the elements. But in the problem of this definition is, in general, this expectation threshold is hard to find. So in the previous examples, those examples were like simple ones. So maybe for those examples, we can find the expectation threshold. But in general, if F is just arbitrary increasing family, then I don't have a good idea for finding the expectation threshold for F. Anyway, so using this definition, we can now rigorously state the Kahn-Kalai conjecture. So the conjecture.
Okay. Summarizing the statement you made in the previous slide, we understand that if you contain something, you have to contain everything smaller than it. So that's what we have to, that's the gist of the definition of Q. And in the case of containing a fixed finite graph, we may look at all its subgraphs and how to contain them too. But if what we want to contain is maybe a large graph, maybe a spanning subgraph, or just an arbitrary family, it's not clear how we would go about considering all their subgraphs. And,
yes, exactly. Yes. So that was the hard part. That is the hard part. Anyway, so thanks for the comment. And so using this definition, now we can state Kahn-Kalai conjecture more rigorously. They said that there exists a universal constant K, which does not depend on anything, such that for every finite set X and increasing family F into 2 to the X, the threshold PC of F is at most this constant K times the expectation threshold times log of the size of the universe. Okay, so this again, this Q of F comes from the expectation the expectation calculation, and this comes from the coupon collector-ish behavior. Here are 2 remarks. First of all, this conjecture is very strong. It implies many hard results, and also it's beautiful. So there are only 2 factors that affect the threshold. But on the other hand, the obstacle is, as Avi said, what's G? If F is any general, like any arbitrary increasing family, then how do we find G? And how do we start our proof using the given G? So the next part is about our work with Frankston, Kahn, and Narayanan. So this is a fractional version of Kahn-Kalai conjecture. So this will be something new. And before we move to this, are there any questions about Kahn-Kalai conjecture? Are you okay? Okay, thank you. Okay, so first, let me define the fractional expectation threshold. And the first part is just recalling the definition for the expectation threshold. And this part, this will give us the definition for the fractional expectation threshold. And basically, this is a fractional version of the definition of the expectation threshold. So it says that Q gives us a lower bound on the threshold if there exists such function. And when we look at this function, one example for this is just the indicator of G. So the picture was like this. We have F, and we have some G here. And this definition uses the existence of G. And here we just make it like fractional version. So the definition is this: if there exists some weight function alpha from 2 to the X to positive numbers, such that first we have this property, which says we have F, and whenever we choose an element in F and we look down and we look at all of the sets below S and then add up the weights of all of the subsets of S, then this is at least at least 1. This part corresponds to number 1. So in number 1, we said whenever we look at we pick up some element in F, and when we look down, there is an element in G contained in S. It was the version in the expectation threshold, but in this fractional expectation threshold, we use the weight function. Second, so item 2 is a fractional version of item 2 here. So this means we consider all of the sets here and consider this weighted sum of the weight. So alpha t times q to the t. If we add them up, then it's at most 1/2. So again, this is a fractional version of this. So here we used, so here what we required was if we sum up this expression for all of the s's in G, then we have this sum at most 1/2. But we just, make it a fractional version and we apply this weight. But again, a motivating example is to just considering alpha equals the indicator of G. Let me give you some time to observe this definition, but are there any questions? So here, this Q will give us a lower bound on PC, but let me not justify it because we already did similar calculation in the previous slide here. So basically their calculation is the same. So let me skip the calculation, but what's important is if we define Q in this way, then this gives us another lower bound on PC. So we take the maximum of Q with such weight function for the definition of the fractional expectation threshold. And so we will not use this definition. What you need to remember for this talk is just this definition is so complicated and we'll not see the definition again. Anyway, so what's important to remember is this. So trivially, Q, the fractional expectation threshold is at least the expectation threshold, right? Because it takes the maximum and this is trivial. And as I said, this fractional expectation threshold gives a lower bound on the threshold. This part I skipped the justification, but it's simple. So let me say this is easy. And using this fractional expectation threshold, we state a conjecture of Talagrand. So let me remind you, we have this Kahn-Kalai conjecture, and Talagrand's conjecture is this. We need one more definition. Sorry, there are so many definitions. So here, L of F, this is the size of a largest minimal element of F. So for example, okay, if our F looks like this, then to find L of F, we look at all of the minimal elements in F and we take the maximum. This. So for example, if F is to contain this H, then L of F is just 5, the number of edges, because all of the minimal elements is 5 uniform. And if F is the set of is to contain the perfect matchings, then L of F is n over 2, the size of the perfect matching. In this case, all of these cases are uniform. Okay, so with this, Talagrand conjectured this statement, which was proved by Frankston, Kahn-Kalai, and myself. Okay, so we showed that there exists a universal constant K such that for every finite set X and increasing family F into 2 to the X, this threshold is bounded above by this constant K times the fractional expectation threshold QF times log of L of F. So this looks similar to Kahn-Kalai conjecture, but we replaced Q of F, the expectation threshold, by QF of F. So that means this part is weaker because in the previous slide, I said Q of F is a lower bound on the fractional expectation threshold. So that means this part is weaker, right? On the other hand, this part is slightly stronger because we don't have to consider the entire size, the size of the entire universe. We just look at the minimal elements. Okay, so let me give you some remarks. First, in many cases, for example, all of the examples that we have seen so far, the expectation threshold and the fractional expectation threshold have the same order. So basically, that means Kahn-Kalai so in this case, Kahn-Kalai conjecture is equivalent to Talagrand's conjecture or FKMP theorem, right? If we don't care about the constant. So this conjecture or FKMP theorem is still very strong. And I can say that up to now, everything implied by Kahn-Kalai conjecture is also implied by FKMP theorem, because all of those cases, no, let me take it back. Let me take back the last sentence and just say everything implied by Kahn-Kalai conjecture can be solved by FKMP theorem. And third, so if L of F is a constant, then we have this, the threshold. Oh yeah, it says that the threshold is in the same order of the fraction expectation threshold because this part is a constant. So this was the question that was raised before. If all of the minimal elements, the minimum h or the size, so if the size of h is a constant, then this FKMP theorem implies that the threshold is in the same order of the expectation threshold. So this nails down the exact threshold. And the proof of this theorem is 4 pages. So this is, I think this is a nice part about our work. And we'll see, if we have time, we'll see a little bit of the proof at the end. And the proof is motivated by Alves et al. About the sunflower world conjecture. But unfortunately, we don't have Ryan today. Okay, so these are some remarks. And in the rest of the first part, first, we'll see some relationships between the expectation threshold and the fraction expectation threshold. And then we'll see some applications of FKMP theorem. So before we move on to that part, are there any questions? Why are you smiling?
Because I'm happy.
Oh, okay. Am I making you happy?
Yes.
Oh, okay. I'm so happy.
Are you going to tell us what the constant is later?
Oh, that's a very good question. The answer is we don't know. So first of all, we didn't try to optimize this constant just as usual. And second, okay, I will talk about it in the next slide. Okay, any other questions? Okay, the next part. So next part is about the difference between the expectation threshold and the fraction expectation threshold. So this part is kind of a digression compared to the rest of the talk, but it had some interesting open questions. So let me talk about it. Please allow me to talk about it. So at this point, when we look at Kahn-Kalai conjecture and FKMP theorem, you might be curious about what's the difference between the expectation threshold and the fraction expectation threshold. And actually, there is a conjecture by Talagrand about the difference. Talagrand conjectured that there exists a universal constant k such that for every finite set x and increasing family f, qf, the fraction expectation threshold is bounded above by some constant k times the expectation threshold. So let me remind you that a trivial lower bound of qf was qf. Right? So this means basically, if this conjecture is true, then that means basically the expectation threshold and the fraction expectation threshold are the same thing up to a constant factor. And so that means this conjecture implies the equivalence of Kahn-Kalai conjecture and FKMP theorem. But this conjecture is very hard. At least for me, it was very hard. So it is the second remark. Even simple instances of this conjecture are not easy to establish. So for example, Talagrand himself showed that his conjecture is true if the weight function alpha, so this alpha is the weight function in the definition of the fraction expectation threshold, but you don't have to remember what the definition is. Anyway, so if this alpha is supported on singletons, then this conjecture is true. So this is a very specific, like easy spatial case, but still the argument for this part is non-trivial. And then in the same paper, Talagrand suggested the below two test cases. First one is when X is this specific universe and alpha is this specific weight function. And this case was resolved by the Marco and Kahn in 2015. And again, this argument was already not trivial at all. And then the second test case is when alpha is supported on two element sets. So this one is less structured, but still very specific. It was not so easy, and Keith Frankston, Jeff Kahn, and myself did this very recently. But even if we did these two element cases, we still don't know how to handle like triple cases, for example. So our initial plan was to apply some inductions, but it's still it's not clear for us how to do it, how to continue. So, but yeah.
I just want to make a comment about this conjecture. Again, I find it extremely bold, the Talagrand conjecture. In the general context of integer programming and linear programming, which is sort of the relation between the original definition Q of f and the refined one with the fractional one, you have something for which you want an integral solution, like a family G that exhibits the lower bound, and you want a weighted or fractional. You extend. You let your variables not take 0, 1 values, but take arbitrary real values, and that's a standard relaxation of an integer program to a linear program. And the gap between the two in lots of examples is large, of course, and in some examples it's tight. And here's a vast family of integer programs, all the graph properties, for which Talagrand claims that there is no gap at all, that the fractional solution is a constant away from the integral solution. Yeah, it's an amazing conjecture. I don't, yeah. My intuition somehow, yeah.
Do you think the conjecture is true?
No, it's not that it's not that I just find it very bold.
Yeah.
It will be, it will be great if it's true, and maybe there's some weird thing where it's not. I don't know. And then we learn that the whole thing is, it's a subfamily of all properties.
Okay. Okay, thank you for your comments. And are there any comments or questions or complaints? Are we okay so far? Because I'm now I'm moving to application part. Okay. So this is about the application, but let me first start with something simpler. Okay. So basically we want to calculate the fraction expectation threshold. Eventually we want to apply FKMP theorem to bound or to nail down the threshold. But for that, we first need to calculate the fraction expectation threshold. But as you see here from the definition, calculating the fraction expectation threshold is not very easy. But here is the lifesaver. Okay. So in the third example, we wanted to find the threshold for a perfect matching. And so the answer that we wanted was this. We wanted to show that the threshold is in the order of log n over n. And a trivial lower bound is already log n over n because of the isolated vertices, the coupon collector problem. And FKMP theorem gives this upper bound. It says that the threshold is bounded above by the fraction expectation threshold times log n, which means as soon as we can show that QF, the fraction expectation threshold, is at most 1 over n, then we are done. It gives an upper bound which matches with the lower bound, right? So in general, when we apply FKMP theorem, what we concern is finding a good upper bound on the fraction expectation threshold. Is this clear? So mainly we are interested in finding on a good upper bound on the fractional expectation threshold. And then the point is, the notion of spread of a hypergraph provides an upper bound on the fractional expectation threshold. And this is where our theorem meets the AOS et al. Result on the sunflower conjecture. So
question now, yeah, just you're in the fractional version of linear programming, and you can use duality to
yes.
to find the value. You know that there is a dual, and you are looking for this upper bound, and you have just an upper bound to prove.
Okay. Oh yeah.
Lower bound. Yes.
Thank you. So here I will give you some practically how we can find an upper bound on the fractional expectation threshold, which is gotten by the notion of spread of hypergraphs. So let me explain first what's the spread of a hypergraph. So here we use H for a hypergraph on X, but repeats are allowed, which means this hypergraph H can be a multi-hypergraph. And usually our H consists of all of the minimal elements of F. So F is the offset generated by H. So for example, if F is the property to contain like H, this graph, then our H is just the copy of H's. Okay. So if F looks like this, we just collect all of the minimal elements in this family F. Okay. And once we have a hypergraph H, we say H is Q spread if it satisfies this property. Namely, so this is my universe 2 to the X, and I have a hypergraph H. Now we are not considering an increasing family, we just look at a hypergraph H. And here, whenever we choose some set I, and we look up, so we consider all of the elements in H which contain I, then the fraction of this shaded part is at most some some quantity Q to the I. So this is bounded above by something, okay? So basically this means that the hypergraph H, the elements of H, cannot be concentrated above some specific element I. So whenever we look at some element I and we look up, then this part, the fraction of this part is not so large. That's the basic thing. So here spread means really spread. The elements of the elements of H is well spreaded.
So in particular, if H was sort of random, that's what you expect.
And also here, so this exponent is quite natural because, for example, if the cardinality of I is small, like here, then it contains more elements, which means this fraction is large. But if the size of I is large, then I is not contained in so many sets. So this I here in the exponent is a natural choice. And also it's very useful in many calculations, but anyway. So one more time, we say a hypergraph H is Q spread if the fraction of elements in H containing I is bounded above by some quantity to the size of I. Okay, so the basic theme is the elements in H cannot be concentrated above a certain element in X. So some certain set in X. Okay, and let me show you how to calculate the spread. So for example, let's say our hypergraph H is the collection of perfect matchings. Then for example, if we look at some single edge, then what's the spread of this single edge? First, we look at this fraction. So this fraction means what's the fraction of perfect matchings which contain this given edge? And that's more or less 1 over n, because once we are given an edge, then it kills all of the more or less n choices out there. So the fraction of perfect matchings, excuse me, which contains this given edge is more or less 1 over n. So this means the spread of this edge is 1 over n, sorry. Then how about the spread of 2 edges? Again, once we are given 2 edges, then it kills more or less 1 over n squared choices, right? Because it kills n choices, it kills n choices. So the fraction of perfect matchings which contain the 2 given edges is 1 over n squared. And from here, we have, because here we have n vector, I think it's more convenient to write in this way. H intersect I divided by H to the 1 over I is at most Q. So if we use this expression, then we have 1 over n squared to the 1 over 2, because we have 2 edges. So this gives us, again, the spread is 1 over n. Okay, and again, if we have like, oh, let me do this later. Anyway, so in this way, we can show that the spread of this hypergraph is E over, more or less E over n. This means if we consider F to contain perfect matching, then we know that by this calculation, we have QF of F is at most the spread of this hypergraph E over n. This was the observation by Talagrand via, so through LP duality, as Avi said. So here, the observation is if the hypergraph H is Q spread, then the fractional expectation threshold of F is bounded above by Q. And this is, I think this is exactly what Avi said. So here, in the definition of the fractional expectation threshold, we have a bunch of linear inequalities. And if we apply this LP duality, then we can get this observation actually. But this observation in the box is more convenient version for us to calculate or to give an upper bound on the fractional expectation threshold. So what we can really get from the LP duality is this. We can say that the fractional expectation is essentially the least Q for which there is a Q spread hypergraph H inside F. But that means once we have a Q spread hypergraph H inside F, then whatever that H is, the Q gotten by H gives an upper bound on the fractional expectation threshold. So in particular, in this example, we just took H to be the minimal elements of F. And it turned out that gives us a good upper bound on the fractional expectation threshold. So this observation, I will not justify this. Because this is not the point of my talk, and also there's not so like enlightening part. It's just LP duality. But one thing that we can remember is from this we have a way to give a good upper bound on the fraction expectation threshold, and then combine this with FKMP theorem, we can nail down, or we can at least give an upper bound on the threshold. Okay. So the first famous application is hypergraph perfect matching. So let me explain this. So here our universe X is now R tuples. So we have n choose R, and we assume that R divides n just to make the notion of perfect matching natural. So here we have a bunch of R tuples, and we choose each R tuple random with probability P independently. So our XP is a random R uniform hypergraph. And again, F is the property to contain a perfect matching, where a perfect matching is just what you think. We have disjoint R tuples, which covers all of the vertices. And again, an easy lower bound is this, which is gotten from the isolated vertices, the coupon collector problem. And for a long time, people thought that this trivial lower bound should be the truth. And this conjecture was famously proved by Johansen, Kahn, and Wu in 2008. So they showed that indeed, this trivial lower bound is an upper bound. So they nailed down the threshold for the random hypergraph perfect matching. But now this result, this hard, famous result is immediately follows from our FKMP theorem, because when we consider this H, which consists of all of the minimal elements in F, then we can easily show that this hypergraph is this quantity spread. So that means here, QF for this hypergraph, for this increasing property, is at most n over e to the 1 minus r, where e is irrelevant. And then this gives us log n. So we have the same result in 4 pages. So yeah, so this is one famous or one nice application. But are there any questions about this application? Am I asking so much? So should I stop asking? Okay, are you okay? Okay,
yeah, ask whenever you want, and if nobody complains or asks, then obviously people are happy and you can continue.
Okay, so this was the first application, and the second application is something new. So the first application was something already known, and the second application was about a conjecture. So in this application, we consider some bounded degree subgraph. So now we are back to our usual universe, n choose 2. So XP is the Erdos-Renyi random graph GNP. And okay, so here our H is a little bit different. H is a given graph on N, but this is not fixed. So this, we can consider it as a spanning graph with maximum degree D. This is a constant. So so H is some fixed spanning graph with bounded maximum degree. And our property F is to contain a copy of H. Okay, so when we look at our F, so this is 2 to the X, and F is here, and F looks like this. So we have all the copies of H's here, and F consists of the offset generated by H. Okay, so in this case, for example, one example for H is this clique vector, which means we have disjoint copies of cliques, KD plus 1, KD plus 1, dot, dot, dot. So this is a spanning graph with maximum degree D. And in this case, what's the threshold? And the threshold is gotten by the combination of the work of Kahn, Riordan, and Haeckel. All of the work, I mean, they are independent work, but when we combine the results, then we can get this precise threshold. So far, we just considered the order of the threshold, but this is a precise result. So you can see here the constant factor and something, but of course you don't have to look at them, just have the impression that, I mean, this is what it should be. So again, this was a natural guess for the answer, and Kahn, Riordan, and Haeckel showed that this is indeed the answer. Anyway, so this is just one example, but what if we consider any general H and compare the threshold for this general H to this specific result? What can we say about the threshold? And people's guess was, so when we consider any spanning graph with maximum degree D, one natural thing is this KD plus 1, sorry, the picture is here, this KD plus 1 factor is the most structured one, which means it's the hardest to get in the random setting. So here what we are doing is just to throw edges at random, and we see at which point we have the desired graph H. So if H is highly structured, then it's natural to guess that it's the hardest to get. So people guessed that this KD plus 1 factor is the hardest one to get, which means if we consider any spanning graph H with maximum degree D, then the threshold for that H must be smaller than the threshold for this clique vector. Am I making sense? In other words, it's the hardest to get the clique vector among all of the graphs with maximum degree D. So the official conjecture was out in 2017 by Ferber, Low, and Nguen. So they conjectured that indeed for any such H, the threshold for this H to contain this H is bounded above by some constant times this star threshold here, the threshold for the clique vector. So it looks that this conjecture is not so old, but I heard that just people naturally thought this should be true for a long time, but it was just not be written in this literature. Anyway, but if we combine FKMP theorem and the above result by Kahn, Riordan, and Haeckel, then we get this stronger result. We can show that the threshold for any graph H with any such graph H is bounded above by 1 plus little o 1 times this star threshold. So this is a very nice result, and this really proves what people think is natural. But I'll skip the details. Oh, Lisa, any questions?
Yes. So I guess in your FKMP theorem there are these log factors.
Mm-hmm.
So do these logs just cancel out with the other factor or something, that you don't get too many logs in the end? Because in your P star, there's not there isn't even a whole log basically.
Oh, yeah, that's a good question. So actually what we do is we didn't use, okay, so let me just briefly explain what we can do. So when we have H, because H has maximum degree D, it has some click like here, and it has some non-clicks. Right? The entire H will look like this. And this part, the clique vector part, will be handled by KRH. So we don't do any calculation for this part. And this part, we can show that this part has better spread, which means the fractional expectation threshold for this part is much smaller than P star. Okay, and then we are done. It sounds simple, but it's not as simple as it sounds, but that's a big idea. Okay, thank you for the question. Are there any other questions?
So does this, so you mentioned this intuition that like the clique is sort of the hardest to get. Does this sort of prove that, or does this sort of just go with, sort of match the intuition that it should be?
Yeah, I think the latter is more correct. So people just naturally thought this should be true, and it turned out we can prove that this is true. Okay, any other questions? Oh, okay, so I think it's good time to take a break. Yeah, so now is the end of the first part.
We are ready for you to continue, Jinyoung.
Okay, thank you. So this is the second part of my talk, but before we start the second part, let me summarize what we have done so far. So the central question that we are considering here is this: given an increasing family F, what's the threshold for F? Namely, for what probability does F happen like more likely or less likely? And trivially, the fractional expectation threshold gives a lower bound on the threshold. And FKMP theorem says that here the fractional expectation threshold times this log factor gives an upper bound on the threshold. So that means the threshold of F is basically trapped between something and something. But there is still this log gap. So the natural next goal is this: to understand the gap between the fractional expectation threshold and the actual threshold. So for example, we can ask such questions like in what case we have the gap, or in what case we do not have the gap, or in what case we have some smaller gap between the fractional expectation threshold and the actual threshold. So here, our main work is to nail down the threshold for the square of a Hamilton cycle. But first, I will first introduce what this means, and then I'll put this question in the context of this goal. So for me, this question was interesting because it was an example to explore this goal, understanding the gap. But first, let me define what a Hamiltonian cycle is and what's the power of a Hamiltonian cycle is. So a Hamiltonian cycle is a cycle of length n. So again, the vertex set is n. So a Hamiltonian cycle is a cycle which covers all of the vertices. And Erdős and Renyi in 1960s asked this question: what's the threshold for for H and P to contain a Hamiltonian cycle? And let me use just PC of HC for this property. And so this was a famous question, and there are a lot of results regarding this. But let me just state this one. So basically, this question was answered by Posa in 1976, who showed that the threshold for the Hamiltonian cycle is in the order of log n over n. So this one looks pretty much familiar. So you can guess that 1 over n is the expectation threshold, and we have this log n from the coupon collector behavior. Anyway, so this was a famous result, but now it's easy from FKMP because we have this upper bound on the threshold. So I think maybe this is redundant, but let me do this calculation because I want to compare this calculation with something else in the future. So for example, let's say, So let's say H is the family of Hamiltonian cycles. And let's calculate the spread of this hypergraph. So for example, if we consider I on a single edge, then what's the spread? The definition of spread is here. In this case, so the fraction of Hamiltonian cycles which contains this given edge is again 1 over n. So this says that the spread of a single edge is 1 over n. On the other hand, if we have like 2 edges or like several edges, it doesn't matter. But in this case, again, it kills. So for example, let's say I is 2 edges. In this case, the fraction of Hamiltonian cycles which contain those 2 edges is more or less 1 over n squared because each edge kills n choices. And then we have this 1 over I factor. So we have 1 over 2, which gives us again 1 over n. And finally, if I is the entire Hamiltonian cycle, like this. In this case, what's the spread of this cycle? This is simply, the denominator is just 1. There is only 1 Hamiltonian cycle in H. So this is 1 over H to the 1 over the size of I, which is n. Are you okay? I just plug in everything to this expression. Are you okay? So what's this? The size of H, what's the number of Hamiltonian cycles in Kn? We have n minus 1 factorial divided by 2, because we can flip it. We have n minus 1, and flip it. So we have n minus 1 factorial over 2. This is more or less n over e to the n. So this spread calculation gives us e over n, which is again 1 over n.
So it is essentially the same calculation as for the perfect matching.
Yes, exactly, yes. But I wanted to compare this with the power of Hamiltonian cycles. Anyway, so my point is here, like, just whatever subset we look at, it gives us kind of like a uniform spread. It always gives us 1 over n. Okay, then let me define the power of a Hamilton cycle. First, the kth power of a Hamilton cycle, here, let me write it hc to the k. This is defined in this way. First, we start from a Hamiltonian cycle, and then we add some edges so that each vertex is adjacent to the vertices with distance at most k. So let me write it bigger. So again, we start from this Hamiltonian cycle. 1, 2, 3, dot, 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 dot. Let's say just this is 1n. Then the kth power of a Hamilton cycle is just we add some edges so that each vertex is adjacent to the vertices within distance k. So here, add this, and add this, and add this up to distance k. And also it goes to here, 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 up to distance k. And we do it for every vertex.
And the notion of power is very natural. It's just the power, the case power of the adjacency matrix of the Hamiltonian cycle.
Yes, yes. Okay, so this is the case power of a Hamilton cycle. And in particular, the square of a Hamilton cycle looks very nice. It looks like this. So we have a bunch of triangles here, right? And so if we started from this 1 up to n, then the square of a Hamilton cycle looks like this. Here we have 1, 2, 3, 4, and here n minus 1, dot, 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 right? So I just add edges to the second neighbor of each vertex. So it looks nice. It's a nice triangle cycle. Are we okay? Okay. Again, the question is, I think I'm asking this question like thousands of times in this talk. What's the threshold for hc to the k? Namely, the threshold for GNP to contain a copy of the kth power of a Hamilton cycle. And again, this calculation is again thousands of times. The expectation calculation gives us this expression. So the threshold for the expectation is n to the 1 over k, which gives us a lower bound on the threshold. But unlike the Hamiltonian cycle case, this case, there's no obvious local obstruction, which means, so in the Hamiltonian cycle case, the threshold from the expectation calculation was 1 over n. So I'm just reminding you now. So when we calculated the expectation, then the trivial lower bound gotten from that calculation was 1 over n. But there was another trivial lower bound, which was log n over n. Right? This was from the expectation calculation, and this was from the coupon collector problem. So if the probability, for example, if P is in this range, then typically there exists some isolated vertices, which forbids the existence of a Hamilton cycle. Okay. But if K is at least 2, so for example, if K is 2, then this is n to the negative 1/2, which is much larger than log n over n. So n to the negative 1/2 is here. So that means if P is in this range, so larger than n to the negative 1/2, then typically all of the vertices have large degrees, which means we don't have to worry about these isolated vertices or some local obstructions because a vertex already have lots of neighbors. Does this make sense? So in this, the Hamiltonian cycle problem, the obstruction was the isolated vertices. So when we look at a single vertex, then there is a positive chance that this vertex is isolated. On the other hand, if K is at least 2, then this probability is large enough to remove all of these obvious local obstructions because a vertex already has lots of neighbors. Am I making sense? Okay.
Very.
Okay, so at this point, a natural guess is maybe this expectation calculation gives us the truth. So the natural guess was the threshold for hc to the k is in the order of n to the negative 1 over k, the threshold from the expectation. Let's see the history of this work. So when k is at least 3, then this question was answered by Riordan in 20 years ago. So he showed that the threshold is indeed in the order of n to the negative 1 over k, and his proof uses the second moment method. But strangely, when k is 2, this problem was pretty resistant. So for example, Kuhn and Osnes in 2012 gave this upper bound on the threshold. And basically, when k is 2, the naive second moment method doesn't work. But I'm not saying that Riordan's work is a naive second moment method. His work is very nice. Actually, he showed something much more general, and this hc to the k were just some examples of his work. Anyway, so Kuhn and Osnes gave this upper bound, which matches with this lower bound in terms of the exponent. But there are still this little o of one term in this exponent. So this is not precise threshold. And after that, Nenadov and Skorich, I'm sorry, but I don't know how to pronounce these names correctly. Anyway, so they showed that they improved this upper bound using this log to the 4 vector. And after that, this upper bound is improved to log cubed. And so here, this is the publication year, and this is the archive year. So this is not anti-chronological. And after that, in Montgomery's unpublished lecture notes, he showed that he improved the upper bound using log squared. And all of those results use something called absorption method. So, but let me not talk about this because I'm not an expert of this method. But what I want to say is, so here, after here, the method that we used is very much different from the method that was used in the previous work. So FKMP gives this upper bound. So now you see where this comes from. You know, this is the fraction expectation threshold, and this is the log vector. But still, the guess was this should be the truth, and this is our main result for today. So together with Jeff Kahn and Bhargav Narayanan, we nailed down the threshold. We showed that the threshold for this HC2 is in the order of n to the negative 1/2. So as you see from this list of improvements, this question itself is pretty interesting. But first, I want to put this in the context of FKMP, or our next goal, to understand the gap between QF and the threshold. Any questions? Are you okay? Okay, first, let me remind you that we said hypergraph H is Q spread if it satisfies this property for any subset in X. And we say the spread of H for the smallest Q, which satisfies this property. And when we look at H, the hypergraph consisting of the power, what's this? The square of a Hamiltonian cycle, then its spread is this. And we can see that, we can see it from this example. Let me show you the calculation. For example, if we consider the entire square of a Hamiltonian cycle, let me just call this HC2. It's hard for me to say the square of a Hamiltonian cycle. Anyway, so when we just look at HC2, so let's say our I is HC2, then the spread of this is simply 1 over the size of H to the 1 over 2n. Do you see it? Because the number of, so HC2 looks like this. So that means every vertex has 4 neighbors. So the number of edges is 2n. Let me just say the number of edges is 2 times n. So we have 1/2n factor here. And here I calculated the size of h, which is n/e to the n. So from here we have more or less e/n to the 1/2, which gives this. And because the spread is the smallest q, so we cannot do better than this calculation. And actually we can show that the worst spread is achieved by HC2. On the other hand, this is the part that I said, I want to compare the calculation. On the other hand, what if we consider I a single edge? In this case, if we calculate the spread, then what we have is, so again, because we have a single edge, so it kills more or less n choices. So the fraction of HC2s which contain this given single edge is more or less 1/n raised to 1/1, which is 1/n. You see that this is much smaller than the spread of h, square root of e/n, right? And this is the same even if we consider something else. So typically when we consider some small number of edges, typically these are all like disjoint, right? Unless the size of I is very large. And if we consider like spread of some single edges, disjoint edges, then we have the spread 1/n, which is much smaller than the spread of the hypergraph itself. So from here, we guessed maybe we can use this, like ununiformity of this spread in the proof of this theorem. That was our motivation. And also we thought this is why this is why this problem is interesting in terms of investigating the gap between QF and PC. Are we okay? So are we okay with the ununiformity of the spread? Okay. And let me raise another interesting example. So here, so this is another case that the gap is not tight and there is some ununiformity of the spread. Okay, so let's say this time H is a triangle factor. So this means we have disjoint triangles which cover all of the vertices. And again, F is the increasing property to contain a copy of H. Then again, the famous Johansen-Kahn-Wu work showed that the threshold for this property is in the order of n to the negative 2/3 times log of 1/3, log to the 1/3. And if we calculate the spread of this hypergraph H, then the spread of this hypergraph is this. And this spread is achieved by disjoint triangles. But typically, if we consider, for example, a single edge, then we have a much smaller spread. So in this case, the spread is not uniform, and we have this strange gap, right? So FKMP gives the gap log n. But here we have much smaller gap, log 1/3. And so far, we don't know where this gap comes from. And one very interesting question for me is, can we prove this Johansen-Kahn-Wu result using this FKMP-ish way? So this is one question that I'm very interested in now. Anyway, but let me continue to the proof. So, okay, so let me give you some sketch of the proof. So basically what we want to prove is this statement. So the statement is the threshold for HC2 is in the order of n to the negative 1/2. But what we show is this: for any epsilon, for any given epsilon, there is a constant k such that if p is larger than this constant times 1/square root of n, then for this P, the probability that GNP contains the square of a Hamilton cycle is close to 1 for sufficiently large n. Okay, so this means, so we are claiming that the threshold is 1 over square root of n. And this theorem says that if indeed P is somewhat larger than this threshold, K is some large constant, K times square root of n, then it's likely for GNP to contain the square of a Hamilton cycle. This is our statement. Okay, and once we show this, then we are done because we know that this 1 over square root of n is a trivial lower bound. Are we okay, or anything unclear? So what we are gonna do is for this P, some large constant K times 1 over square root of n, we look at GNP and we show that with large probability, with probability close to 1, this GNP contains a copy of the square of a Hamilton cycle. That's what we are gonna do in the proof. Okay? Okay. So here again, our universe is X and choose 2, the set of edges. And our hypergraph is copies of HC2s. And let me call them S1, S2, just for simplicity, just for convenience. And we generate GNP in 2 rounds. So our G will be the union of 2 random sets W0 and W1 with W0, W1 has this probability distribution where alpha is another constant times 1 over square root of n. So this means, so for GNP, we can look at it as like we are throwing some edges randomly with probability P. And I'm saying that we do it 2 times. So this is our universe. And in the first round, I will throw some random edges with probability alpha this time. And in the second round, I throw some random edges again with probability alpha. And if I take the union of them, then still it's some constant times 1 over square root of n. Even if, so here, eventually this constant K is something like 2 times K squared, K prime. It doesn't really matter because K is always a large constant. And our goal is to show that there is some S. This is a copy of HC squared. There is a copy of HC2 such that this copy is contained in the union of W0 and W1, which is eventually our random graph GNP. Is it clear what we are doing?
So they I never got any communication.
Okay. So we throw some random edges twice, and our goal is to find a copy of H squared among those edges. Looks very, okay.
Well, they ask about maybe actually you don't need to unless you change, but you need to do the coordination of benefits. They don't tell you that every year. Remember they cancel my insurance? Oh, I did it and then.
Okay, may I continue? Avi, are you okay?
Yeah, no, I don't hear. There is somebody talking, and I don't know if it's a question or it's just again something else that is unrelated.
I heard the word insurance.
Yeah, so insurance is probably not directly related to threshold.
Okay, yeah, this is not finance.
Yeah, I just want to say, it's a thought experiment. Anyway, we can think of G as the union of 2 random graphs like this. We are allowed to think it as we wish.
Yes, okay, thank you. Okay, so this is just a repetition. We generate G in 2 rounds, and our goal is to contain at least 1 copy of HC2 in our union. And when we look at this plan, so we'll do this in 2 rounds, what one may dream is this. So this is a dreamy situation. In the first round, we have some randoms at W0, and we hope that, or we dream that this W0 is some large fraction of each S's. So, H is S1, S2, ... So here H means a copy of HC2. And in the first round, we dream that we have a copy of S, HC2, and we have some randoms at W0. And the size of S is 2n, and the size of W0 is more or less n, some large constant times n root and square root of n, because our universe has size more or less n squared, and our probability is some large constant times 1 over square root of n. So the typical size of W0 is some constant times n square root of n. So that means the size of W is much larger than the size of S. So one may dream that because we have such a large random set, so typically H0 is some large fraction of each S's. And of course, this is the dream, and I will say that this cannot be true. In the next line, I already said it's too dreamy. Anyway, let me continue for the motivation. So, and once this round 1 happens, then in round 2, the picture may look like this. We have our universe X, and here we have our randoms. We already had our randoms at W0. And if the dream in the first round is true, then what we see in the second round is we just see some small fragments from each S's, because in the first round, we assumed that a large fraction of each S is eaten by W0. So let's say if this is S1, a fraction of S1, then the leftover of S1 is already here. If this is S2, then the leftover of S2 is here, like this. And if this dream is true, then because each of Si is very small compared to the size of W0, so we can hope that our second random set W1, which is much larger than the fragments of Si's, can eat at least one of them. And in this way, the union of W0 and W1 eats the entire one copy of S. But as I said at the bottom, this situation is too dreamy, because typically the size of the intersection of W0 and S is more or less square root of n, because we have the size of S 2 times n, and this is random with probability 1 over square root of n. So the typical size of the intersection is very small compared to the entire size of S. So the typical picture is if we have S whose size is 2n, then the fraction of S's which is eaten by W0 looks like this, square root of n, which is much, much smaller than the original size. So this situation is too dreamy, but let me remind you that we just need one S. So here, as I said, our goal is to contain just one copy of HC2, right? So that means it doesn't have to be, so in the first round, we don't have to eat typical, every S's. As long as there is one copy of S which is eaten by W0, then we are happy. We can say that we already made a good progress, because we can pursue contain the leftover of that specific S. Are we okay? So, I'm sorry, Cynthia, you look sad. Oh, I'm sorry.
Really tricky, but good.
Yeah, I'm trying, but yeah, okay. So this is the main point. I have only 10 minutes left, so I think I should do it quickly. Okay, so our main point is this. So really, we cannot hope this to happen for typical S's, But we can say that at least this happens for a certain S. That's what this main point says. So this main point says that for typical pair S in H and W0 in X choose W, with W is the expected size of W0. So here we have S, and we have our random set W0. And as I said, typically their intersection is very small, but we can show that there is another copy of HC2 whose name is J, which is contained in the union of W0 and S, and also J minus W0 is very small, which means there is a copy of HC2 which looks like this. So I don't think I will have time to prove this main point, but I just want to show you the point of this main point. So this says that for typical S, we are not guaranteed to make a good progress, but at least there exists some J for which W0 makes a good progress. That's what this main point says. And we say that the pair SW is good if there exists such J, such good J. Okay, so if the pair SW is good, then there exists another HC2 here, whose fragment here is very small. Okay, and once we believe this main point, then the rest of the proof goes in this way. So this is our reality, actual round one. So this is our universe, and those circles, those are Hamiltonian, HC2s. So we have S1, S2, S3, Okay. And here we sprinkle our first random set W0, which looks like this, because this is random edges. But for simplicity, let me draw W0 in this way. So let's say our W0 looks like this. This is our random set W0. Okay. And when we look at S1 and W0, then typically their intersection is very small. But also because of this main point, for typical members of SI, there is some JI, let me call this J1, which looks like this. And if this happens, then we replace S1 by this part. Let me call this J1 prime. So from H, we construct a new hypergraph H prime, which consists of this little fragment J1.
Jinyoung?
Yes.
Just because S and J look so different, I just want to stress that they are the same thing. The J's are also squares of Hamiltonian cycles. They are just, there are some other S.
How does it look now? Are you okay? Or let me change the color. Yeah, you're right. They look very different. Okay. How about now? J1. So here, S1 is a copy of HC2 and J1 is another copy of HC2, but we are the existence of such J1 is guaranteed by our main point, which we will skip the proof. Okay, so we continue. Now we look at S2, and if S2 is good, good means there is such J2. So we look at S2, and if this is good, that means there's another J2, another copy of HC2, whose fragment is very small, who is eaten by W1 by a lot. And if this happens, then we replace S2 by J2 prime. So J2 prime is the part of J2 which is in the outside of W1. Okay, but it's possible that a certain SI is bad, which means there does not exist such nice, good J. And in this case, we just kick out this S3. This is okay because by this red main point, we said that this is a typical behavior, which means the number of bad S's is negligible. So we can safely kick them out. It doesn't affect the size of H. So we just kicked out S3, and if S4 is good, then also we replace this by J4 prime, ... In this way, we have another hypergraph H prime, which is possibly multi-hypergraph, right? Because the fragment can be equal. We are just taking subsets. That doesn't matter. It's okay to be, for H to be a multi-hypergraph. So what's good about this argument? By doing this, now we have this picture. So let me make it smaller so that you can see the two pictures at the same time. So now we are with the new hypergraph H prime. So this means, so let's say this one is J1 prime, J2 prime, J3 prime, or possibly this is equal to J4 prime. What's good about those fragments is the leftover of these fragments are already in W0 by our definition. So the rest of J1 prime is here, the rest of J2 prime is here, and J3 is here like this. So a significant fraction of each Ji is already in W0. So in the second round, all that we need to do is to contain at least one of such J primes using our second random set W1. And now it's easy because all of the sizes are small and the spread condition. So let me say a little bit more. So in the second round, what we are gonna do is to choose our second random set W1. Okay, and as long as W1 contains at least one Ji prime, then we are done, right? This Ji prime is in W1, and the rest of I, this is I. The Ji prime is in W1, and the rest part of Ji is in W0. Then that means the entire Ji is contained in W0 union W1, which is our GNP. So we successfully contain a copy of HC2 with our GNP. Are we okay? So really the main point was the main point, but here in the second round, still the spread plays a very important role. So when we look at our hypergraph H prime, first of all, this is square root n bounded, which means each element has size at most square root of n. That's gotten from this main point. We said the size of the fragment is at most square root of n. So those are very small. And the main point says that, as I said, the size of the new hypergraph H prime is more or less the same as the size of the original hypergraph. And the spread of H prime is as good as the original hypergraph H. This is because we can look at this expression. So in the new hypergraph H prime, when we calculate the spread, the denominator does not change a lot because, as I said, the size of H prime is more or less the same as the size of H. So the denominator is almost the same. Then how about the numerator? Here, we look at the elements of H which contain I. So let's say in the original hypergraph H, we have I, and we have some sets in H which contains this I. Then what we did in the first round is just take a subset of each SI. So in the new hypergraph, what we have is a subset of SI. So let's say this is J1 prime, or this is J2 prime, dot, dot, dot. So when we look at this picture, this this numerator only decreases because the number of elements in H prime, which contains I, does not increase, it only decreases. So our denominator is almost the same, but our numerator only decreases, which means the spread of H prime is at least as small as the spread of H. Does this make sense? So that's the point. The spread of H prime is as good as the spread of H prime is as good as H, or as small as H. And from there, it's perfect to apply the second moment method. So this is for experts. So this is for people who are familiar with calculation. So as usual, X is the sum of indicator for our random set W1 to contain S prime. And now the expectation of X goes to the infinity because the uniformity is much smaller than the original graph. On the other hand, in our variance calculation, basically we have to find an upper bound on this expression. This is just usual calculation, so let me not explain where it comes from. But in this calculation, basically this is the fight between P to D something and the number of terms. But here, the number of summands is bounded above by this spread condition. Because basically what's in this summand is the number of pairs A, B with its intersection is something like I. And by this spread condition, we have an upper bound on the number of A, B's containing I. So it gives an upper bound on the number of summands here. So it gives us a small enough variance. And eventually, so using Chernoff, we can show that with some reasonable probability, W1 contains a member of H prime, and we are done. So because I'm already over time, let me just say one thing. So here I want to tell you where we use the spread condition. And in the second part, we use the spread condition for the second moment calculation. And the spread condition is very surprising that the spread condition works well with the variance calculation. And in the first part, so basically to get this small fragment, what's essential was the spread condition, but I don't have time to talk about it. So I think I should stop now. Thank you very much for your attention and reaction.
Thank you very much, Jinyoung. I'll work for everybody. Yes, questions?
I have a question. So for the result with the Hamilton square of the Hamilton cycle, do you use your FKMP theorem at all? Or is that basically independent?
Okay, so we do not rely on any existing results in FKMP, but our starting point is given by FKMP. So, or what can I say? Okay, so here in the first round, the main idea was to replace each SI by JI prime. That idea comes from actually Always et al., the sunflower conjecture. But our improvement here was to get this small fragment. So in FKMP, it was about 0.9 times the uniformity of S, which is about like 0.9 times N. So this is significantly larger than square root of N. So basically our improvement is to get this small square root of N. So over there, we used some new idea. Yeah, so after this replacing idea, I think I can say that almost so the idea is very new.
I see. So did I understand correctly? You use a similar idea as in the proof of the FKMP theorem, but you don't use the theorem itself.
Say that again.
So did I understand correctly that one part of your proof for the square of the Hamilton cycle uses a similar idea as the proof of the FKMP theorem, but not the theorem itself?
No, yeah.
Okay. Thank you.
Thanks for your question.
More questions? Just
so when you're
to continue just this question of Lisa, yeah, this idea of eating parts of what you want to cover in rounds is a key thing in the Elwise et al. Work on the sunflower conjecture, and is used in FKMP. And yeah, it's just a much stronger. There you eat a constant fraction, and here you eat almost everything. But there was a question, sorry.
I was going to ask, so in this 2 rounds, the 2 rounds are basically the same size, right? Like W0 and W1.
Yes, yes. Basically, you wouldn't up to a constant.
You know, in it anyhow, right? You could split it into multiple groups. You could split it into groups of different sizes, because you're not using them sort of symmetrically at all.
Oh, yeah. So I think that's a good point. So for example, in FKMP, we use several rounds, and basically this log factor comes from the repetition of the rounds. So we repeated the same round for log n times, and that's where the log n factor comes from. But here, the key point is we removed the iteration. So we just did it in one round, and so that's the key to remove this log factor.
Is there some sort of high-level reason why you would want every round to be the same size, for example?
Oh, I think so. So at the end, we want our GNP, which has some fixed given size. So I'm not sure, but there is some like high-level idea other than the proof works.
It's not I think generality if you are doing just a constant number of rounds, just 2. It's no loss of generality to take them as roughly the same size.
Thank you for your answer.
K is a large constant, so might as well.
Yeah, I don't know. I guess you could have n to the 2/3 in one round and then clean up with. Yeah, I don't know.
Yeah, but why save? Why not take more? You are allowed to take a constant fraction of everything. So
I mean,
they are not fighting to optimize the constant.
Yeah.
So is this a potential example where the second Talagrand conjecture fails?
Oh, no, here the expectation threshold gives a lower bound which matches with the upper bound, which is gotten by the fractional expectation threshold, I think.
Oh, okay.
Yeah, so yeah, my answer is I don't think so.
More questions?
But thanks for your question.
Okay, great. So some of us are meeting at 1 again. So let me thank Jinyoung again for a wonderful lecture, and we'll see some of you soon. Maybe we'll even, if these people want to get lunches, maybe we meet 10 minutes later, like 1:10. And thanks. That was great.
Thank you. Thank you for your attention, and thanks for coming.